So as the frequency of the light increases, the energy of the photon increases. As the wavelength of the light increases, the energy of the photon decreases. And in this case, the blue light with a higher frequency has more energy than red light. Okay, so the photons are, in this case, little particles. We know photons were actually a term that we use to describe electromagnetic radiation. So they behave like particles. It's the particle of electromagnetic radiation. And photons carry energy, just like a moving baseball carries energy. When the baseball hits you, you're going to get hurt. And the photons carries energy when they hit the surface of the metal. As long as you have enough energy, you will be able to transfer that energy to the electrons of the atoms in the metal. And those electrons will be ejected from the surface of the metal there. So in this case, this is the equation that we can quantify the amount of energy there. E equals to H times the frequency, or Hc over lambda. Okay, so this equation, the second equation there, if we give you Planck constant, and Planck constant is something that you don't have to memorize, it's 6.6262 times 10 to the negative 34 joules times second. Okay, so that's the Planck's constant there. If we give you the frequency or the wavelength, we can ask you to calculate the amount of energy carried by a particular photon or particle. Okay, and if we ask you how many energy is carried by a mole of particle, you multiply that number, the energy carried by one particle, you multiply that by 6.02 times 10 to the 23. A mole of any substance has the same number of particles there. That's Avogadro's number. Okay, so that's our second equation there. And again, these two equations there, the constants, something that you don't have to memorize. We'll give you the constants there, but you need to know the basic form of the equation. We are going to ask you to do many different calculations. And here's an example there. We ask you to calculate the energy of 1 mole of photon of red light. Now we're treating photons, we're treating electromagnetic radiation as particles. Okay? So we ask you to calculate the energy of 1 mole of photon of red light at 685 nanometer in the units of kilojoules per mole. Using the Planck's equation there, H times the frequency, or Hc over lambda. In this case, lambda is given, the wavelength. Okay, so you plug in the number, 6.6262, that's the Planck's constant, times 3.00 times 10 to the 8 meters per second. And that's the speed of light. And then 685 nanometer has to convert them into meters, so the meter and meter will cancel out. Now, this part is the energy carried by 1 photon of this particular wavelength. 1 mole of photon has 6.02 times 10 to the 23. And if you multiply all the numbers together and plug in the numbers, and if you do the calculation, plug in the numbers into your calculator there, this is the number you get, 1.75 times 10 to the 5th joules per mole of photon, or 175 kilojoules per mole. Why is this important? This is around the amount of energy, the range of energy that can actually promote chemical reaction. Enough energy is supplied by this kind of radiation to break chemical bonds. The experiment you can do, if you have, say, methane gas mixed with chlorine gas, if you keep them in a dark place, those two gases are not reacting with one another. However, if you take that bottle containing the two gases there, and you put it under the sun, over the time, you will see the color of the chlorine gas start to dissipate. Eventually, the whole mixture becomes colorless, indicating there's a chemical reaction happening there. The radiation from the sun will initiate the chemical reaction. So the radiation carries energy. The energy is enough to break the old chemical bonds and then allowing new chemical bonds to be formed. So energy from the radiation can actually promote chemical reaction, cause chemical reaction to happen. So there's always an energy aspect of the chemical reaction there. Looking at the matter part, and looking at the energy part, in chapter 1 through 5, we're looking at the matter part, and then chapter 6, we look at the energy part there. So this is, based on this particular calculation there, we know that this red light radiation carries enough energy to initiate chemical reactions there. Now the problem using these two equations there now, these is that we can actually compare the amount of energy carried by X-ray and microwave. Okay. X-ray has a wavelength of 1 times 10 to the negative 10 meters per second. Microwave, 1 times 10 to the negative 2 meters per second. If we ask you to calculate the amount of energy carried by these two different types of radiation, all we need to do is to plug in. These two are constants. Constant speed of light. All we need you to do is plug in the wavelength. Now, this is a much bigger number compared to this. So you put a smaller number in the denominator, you end up with a higher amount of energy. So X-ray carries much more energy than microwave. And just so you know, your cell phone actually uses microwave to transmit signal. Microwave is a type of radiation. And you want to be careful when you put that phone next to your brain, on your ear, and talking for hours on the cell phone. And you probably heard this argument all along. Using of the cell phone does not cause any health issues at all. But you need to look a little bit deeper into who sponsored all of that scientific research. You will find familiar names like Comcast, Verizon, AT&T behind it. They try to tell you radiation is not, this low dose of radiation is no harm to your health. Well, we must say there's no definitive answer to that question yet.